This is your presenter Asloob Mudassar, and I am presenting slide number 84 of the course on laser physics. Question is, find an expression for the total number of photons in a given mode at time t after m round trips. Discuss the photon lifetime and also define quality factor for a cavity and express it in appropriate parameters. The answer is, consider a cavity mode that undergoes some losses. For example, diffraction losses, mirror losses, scattering losses due to the presence of the active medium in the cavity. To calculate the rate of energy decay for a cavity mode, we assume I naught as the initial intensity corresponding to the field amplitude E prime of x1, y1 and 0. The intensity of the mode after one round trip which requires a time of t1 equal to 2L over C can be written as, where capital L is the length of the cavity and C is the velocity of light. So after one round trip, the intensity can be given as I of t1, that is intensity at n time t1, that is the intensity after a round trip time t1 is equal to r1 multiplied by r2 multiplied by 1 minus t square and then I naught, where r1 and r2 are the power reflectivities of the mirrors and t is the fractional internal loss per pass due to all possible losses. Intensity is reduced by a factor of 1 minus ti in a single pass and by a factor of 1 minus ti whole square in a double pass. So in order to justify equation number 1, we assume that, for example, there are two mirrors M1 and M2 of the cavity, and R1 and R2 are the power reflectivities of these two mirrors. And suppose that you choose a point within the cavity, for example, just in front of the mirror M1, from where the light is moving towards mirror M1. So when the light will strike the mirror M1 and is reflected, then you see that it will encounter a power reflectivity R1. So the intensity reflected from the first mirror will be I naught multiplied by R1. And then the light will travel throughout the cavity in single pass, encountering an internal loss of 1 minus ti. And then the light will hit the second mirror M2, and on reflection from the second mirror M2 it will encounter a power reflectivity R2. So when the light will go back to the same point from where it started after reflection from the mirror M2, it will again pass through the cavity, so it will have an additional term of 1 minus ti. So multiplying all these terms, you will have I naught multiplied by R1, then multiplied by 1 minus ti, then multiplied by R2, then again multiplied by 1 minus ti. So the equation number 1 is formed. So let me say again that R1 and R2 are the power reflectivities of the mirrors, and Ti is the fractional internal loss per pass due to all possible losses. So intensity is reduced by a factor of 1 minus Ti in a single pass and by a factor of square of 1 minus Ti in a double pass. Intensity after m round trips at a time intensity after m round trips, that is at a time tm, which is equal to m times 2L over C, is given by, you see that 2L over C is the time for one round trip, and for m round trip you are multiplying this by m. In principle you are multiplying m to the value of t1 which is shown over here for one round trip. So the time for the total m round trips Tm is equal to m times into 2L over C, and is given by. So then you see that we are now writing the same expression as given in equation number 1, which was given for one round trip, and then for m round trip we write the same relation as given in equation number 2. So I of Tm is equal to R1 into R2 multiplied by 1 minus Ti whole square, and this whole raised to power m, and then multiplied by I naught. Similarly, the total number of photons in a given mode at time Tm, that is phi of Tm, where phi stands for the total number of photons, and Tm mean that after m round trips. So phi of Tm is related to the initial number of photons phi naught through the following relationship. That is, phi of Tm is equal to R1 into R2 into 1 minus Ti whole square, this whole term raised to power m, and then multiplied by initial number of photons phi naught. So this is what we have written in equation number 3, following exactly equation number 2, replacing the intensity by the number of photons. Now we are going to set this, that is, let us set R1 into R2 into 1 minus Ti whole square, this whole term raised to power m, equal to e to the power minus 2ml capital L divided by C into tau C, and this becomes equal to e to the power minus Tm over tau C, because we have introduced the value of Tm from over here, that is Tm is equal to m times into 2L over C. So introducing that value, we have written the final expression on the right hand side of equation number 4 as e to the power minus Tm over tau C. Now you see that here Tm has been explained, and what is the tau C? Tau C is a constant independent of the number of round trips and is regarded as the cavity photon lifetime. So notice that it is the cavity photon lifetime. That is, the cavity photon will die out after this time, and is given by tau C is equal to minus 2 times capital L divided by C into log of R1 into R2 and multiplied by 1 minus Ti whole square. So you see that this is what we have written, the cavity photon lifetime. We can rewrite equation number 3, that is this equation, as phi of Tm is equal to e to the power minus Tm over tau C into phi naught. So we have introduced this relationship into a relationship of equation number 4 has been inserted in equation number 3, and we have obtained the relationship as given in equation number 6, that is phi of Tm is equal to e to the power minus Tm over tau C multiplied by phi naught. Let us assume that this equation holds at any time t, then phi of t is equivalent to e to the power minus t over tau C into phi naught. So you see that in equation number 6 we have time for m round trips, and in equation number 7 we have taken any time t. The same relationship has been written in equation number 7 for any time t. It could be a t is equal to Tm, it could be any time, it could be the time for round trips, or it could be the any time not related with the round trips. So thus we can write the electric field at the position r and at any time t within the cavity according to this relationship, that is E with the position vector r and time t, that is E of rt is equal to E naught into U of r, where UR is the spatial part of the electric field related only with the position r, and then multiplied by the phase vector, which is equal to e to the power iota omega t minus t over 2 tau c. So there is a negative sign, remember, e to the power iota omega t minus t over 2 tau c, as shown in equation number 8. So this is a form of the general electric field that we have written for such a cavity. So this gives the mode field. The field within the cavity is regarded as the mode field, and phi of t is equal to e to the power minus t over tau c into phi naught gives the number of photons in a cavity at time t. We can also find an alternative expression for tau c as given. So you see that here we have given one relationship for tau c, that is the cavity photon lifetime. C stands for cavity photon and tau stands for lifetime. So tau c is the cavity photon lifetime, which we have expressed in terms of the length of the cavity capital L, the speed of light c, and of course the logarithm of the internal losses within the cavity, which depends upon the power reflectivities of the two mirrors, that is capital R1 and R2, and also depends upon the internal losses of the cavity, which we have described as by the term 1 minus ti whole square due to the traveling of the light for the two passes, that is for one round trip. So that's why we have written tau c over here. But you know that tau c can also be defined as given in equation number 9, that is tau c is equal to capital L over c times into gamma, where we have that is can be written as a tau of capital T, that is tau capital T divided by gamma, and we have written tau capital T equal to capital L over C, that is the cavity photon lifetime is equal to the transit time tau capital T. So capital T, so capital T as a subscript with tau stands for the transit time. So tau capital T is the transit time of a laser cavity divided by the logarithmic cavity loss gamma, which we have defined also earlier. So gamma is equal to log of R1 into R2 into square of 1 minus Ti. The output field leaving the cavity from one of the resonator mirrors has a time behavior similar to the mode behavior inside the cavity. That is, the field outside the cavity will be similar to the field within the cavity. The Fourier transform of the output field gives the power spectrum, which has the Lorentzian line shape with line width at full width half maximum given by delta mu c is equal to 1 over 2 pi into tau c. So you see that if you visit one of my previous slides on the course on the laser physics, where I have calculated the cavity round trip losses within the cavity, then you see you will encounter a relationship over there for example a relationship for tau c, and also the relationship of the losses within the cavity. So this is what you can find out in one of such slides. So again, you can also find this relationship in the same slide that I just talked about. So delta nu c has the Lorentzian line shape with the line width at a half maximum is given by delta nu c is equal to 1 over 2 pi into tau c. So using tau c from equation number 5, this is equation number 5. So I am going to write tau c again from equation number 5, assuming that Ti, that is the internal losses, are completely zero. Then tau c is given by, then I can insert the value of tau c in equation number 7, in equation number 11, and then we have delta nu c is equal to c over 2L into log of R1 R2 divided by 2 pi. So this is the relation that I have written for the line width of the Lorentzian line shape delta nu c, assuming that the internal loss within the cavity is zero, and this is shown in equation number 12. So delta nu c is equal to c over 2l into log of r1 over r1 into r2 divided by 2 pi. We have also obtained delta nu c for such a cavity in which the internal losses were 0. So I am just talking about the Fabry-Pérot interferometer. The transmission spectrum of the Fabry-Pérot interferometer gives delta nu c is equal to c over 2l, and then we have 1 minus square root of r1 into r2 divided by pi times r1 r2 raised to power 1 over 4. So you can consult the previous slides on Fabry-Pérot interferometer. There you can find out this relationship given in equation number 13. So we have, since we in the Fabry-Pérot interferometer, we have considered 0 losses within the cavity, and we wrote down delta nu c for such a Fabry-Pérot interferometer as given in equation number 13. That's why we have also reproduced equation number 12 in the same sense that we are ignoring the internal losses, so that we can compare the result from equation number 12 and equation number 13. In principle, these two results should be exactly equal to each other, but since the parameters are different over here, that's why if you plot delta nu c from equation number 12 and equation number 13, you will see that these results, though difficult, though obviously different in shape, but actually they are very close to each other. So comparing equation number 12 and 13, the discrepancy between the two results is quite small. The cavity line shape may therefore be taken as Lorentzian. So you see that we can take the cavity line shape for both the Fabry-Pérot, interferometer and for the laser cavity that we have just discussed. For both of these cases, we can say that the cavity line shape is therefore Lorentzian. The quality factor or the Q factor of a cavity is defined as the Q factor, capital Q, is equal to 2 pi times energy stored in one round trip in the cavity divided by the energy lost in one round trip within the cavity, where the energy stored is given by energy stored in one round trip is equal to phi into h nu, where phi is the number of photons and h nu is the energy of the photon. So multiplying these two together will give you the total energy stored in the photon in the cavity in one round trip, because here you can consider phi for a one round trip. And you see that we have defined phi for one round trip in one of the previous slides. Either you can set, for example, in one round trip you have this relationship, or you can set the value of m is equal to 1 for one round trip over here, for example, and you know that you have calculated the one round trip time, for example, over here. You can set the value of m is equal to 1 to find the one time for one round trip, or equivalently it is given as t1 is equal to 2l over c. So phi can be defined as, you see that we have given the expression for the phi over here, for example, over here phi in equation number 6, for example, you can set t is equal to m is equal to 1, and then it becomes the number of photons in one round trip. So setting time, so here phi is actually the number of photons in one round trip. So phi in one round trip multiplied by the h nu energy of the photon gives you the energy stored in one round trip. Now we want to calculate the energy lost in one round trip, and for that one we have some tricky relationship, that is h nu, which is the energy of the photon, and then we have to multiply it with the number of photons which are lost in one round trip, and that is given by minus d phi over dt, that is the decay of number of photons with time. And after this derivative, evaluate the time at time t is equal to 1, because for one round trip the time is t1, and then this whole expression within the parenthesis will be multiplied outside by time t1 written in red. so that we can d phi over dt. So this dimensionally we can correct it but by multiplying with the time t1, so that the term within the parenthesis and multiplied with the time t1 will give you the number of photons lost in one round trip in the cavity, and then multiplying by those number of photons with the energy of the photon outside by h nu, we have the energy lost in one round trip. So you can take the derivative of phi with the time t and then evaluate. For example, you can use this expression. For example, equation number 7, you can take the time derivative of d phi over dt, and then you can evaluate that time with the time t is equal to 1, and then multiply that expression with the time t1. You will get this expression. You can introduce t1 can be written as, you see that t1 over here I have defined earlier, which is very simple. That is t1 is equal to 2L over C. If you take and you know that the reciprocal of time t1 is the frequency of resonance, the resonance frequency, which is equal to nu is equal to C over 2L. And the frequency, that the resonance frequency relationship has also been given in the previous slide, that is in the slide number 83. So here you can, if you take the reciprocal of time t1, that is if you invert the formula on the right hand side, that is C over 2L will give you the resonance frequency nu. So I have introduced that one over here in terms of the frequency. So I have 1 over nu over here. So T1 has been replaced by 1 over nu, where nu is the resonance frequency. And you will see that the nu in the numerator will cancel out with the nu in the denominator. And then you have this relationship h phi over tau c. Here this phi gives you the number of photons in one round trip. And again the photon over here in the formula of the energy stored, this phi is also for the one round trip. So both photons have been defined for one round trip. Now the quality factor Q is given by this formula. Q is equal to 2 pi into energy stored in one round trip divided by the energy lost in one round trip. So substituting these two values over here, we have capital Q is equal to 2 pi into phi h nu divided by h into phi, and the frequency 1 over nu has been written as tau c. So you see that here we have tau c over here, you see that, and this tau is in the denominator, and the denominator of the denominator will be written as the numerator. So tau c will be written in the numerator from this expression. So we have phi h nu divided by phi divided by h phi divided by tau c, and we have moved the tau c in the numerator. And you see that after cancellation of the common terms, we have 2 pi nu into tau c. So using tau c from equation number 11 gives you, so you see that we can use tau c from equation number 11, that is from here. You can replace tau c with the representation of delta nu c. Then of course we can write this, write down capital Q is equal to nu over delta nu c. So this is the quality factor of the cavity. The quality factor is thus the ratio of the resonance frequency nu of a given mode to its line width, that is delta nu c. And you see that nu is the frequency, that is we are talking about the resonance frequency nu. So actually we are talking about this mode. So the quality factor is thus the ratio of the resonance frequency nu of a given mode to its line width, that is delta nu c. A very high Q means a very low loss of energy in one oscillations per cycle. So you see that I think that I have answered all the queries made in the question. So the answer is complete. And this is the end of slide number 84.